Okay, welcome again. So today we will discuss about the timing diagrams. But before I go into the timing diagrams, we'll just go through how the microprocessor communicates between the memory and this other input-output devices. So this uh, diagram basically gives you the microprocessor communication and the timing for instruction, which is move C comma A, and the operation code for this is 4FH. Okay, now see, by the time you know what is a processor and how it executes the instructions. Okay, so for every instructions we have a operation code which is stored in the memory. So the processor basically places the address of that memory location on the address bus, which is loaded from the program counter, and then gets incremented by 1. So then that data byte or instruction is basically fetched. It comes through the internal data bus to the instruction decoder, and the instruction decoder decodes it, and then finally it gives some control signals are generated by the timing and control circuit, and that instruction is executed. Okay, so the first part of an instruction is always opcode fetch, right? So this diagram shows how it is executed. So 4F in hexadecimal is the operation code or opcode for this instruction move C comma A, and the purpose of the instruction is to copy the contents of accumulator into register C. Okay, so how it is done? So first of all, the program counter will be loaded by the address of the memory location where this opcode is stored. So assume that this operation code 4FH is stored at a memory location 2005. Okay, so what is the first step? The program counter will be loaded with the starting address of the memory location, that is 2005. Okay, and this address is now placed on the address bus. Of course it is multiplexed. Okay, so you have 8 bits for higher address and another 8 bits for lower address. Okay, so the latch is not the ALE is not basically shown here. So this address bus now carries the address of the memory location, and this memory location gets identified. Okay, the first operation. And once this memory location is identified, the contents of the program counter will be incremented by 1 automatically. Okay, so that it points to the next memory location from which you are going to fetch the next byte. Okay, and once this memory location is identified, the processor will send this control signal which is read. Okay, so this memory chip will get activated, and whatever is the data at that location, that is 4F, it will come on the data bus. Okay, and through data bus, this data will go inside the microprocessor through internal data bus in the instruction register, and from there it will go to the instruction decoder. Okay, now the instruction decoder will decode this instruction, or it will understand what is the meaning of this operation code basically, and it will come to know, okay, that it has to copy the contents of A into C, and then this instruction decoder will give some signals to the control logic. So this control logic will basically activate certain signals which will execute the instructions. Okay, so what it will do basically, what the control and logic circuit will do when it comes to know that it has to copy the contents of A into register C. So first of all, the contents of A will be transferred from A. It will go from A to temporary register. Okay, and then the contents of temporary register will be transferred to register C. Okay, and this instruction will be executed. Okay, this is how the timings are controlled by the processor. Now we will see the timing diagram. So we will discuss now the timing diagrams, which are very important to understand. Okay. So the timing diagrams, they basically indicate how the microprocessors generates various control signals and how all these operations they are executed. Okay, or fetch, decode, and execute, how they are basically operated with respect to the clock frequency. That is shown by the timing diagrams. Okay. Also, you will see that the first operation in any instruction, it is always opcode fetch. Okay. After opcode fetch, there may be some memory read operation or memory write, or it may be some input output read write operation. That is a separate thing. Okay, but the first operation that the processor performs is always a opcode fetch for any instruction. Okay. So like suppose if I give an example, just in the previous case, you have instruction move C comma A. So you have some operation code for that. It is suppose 42H. Okay. Similarly, you have instruction suppose add B, and you have some operation code for it. Let us suppose it is 35H. Okay. And you have instruction suppose MVI A comma 32H. Okay. So this is a move C comma A is a 1 byte instruction. Okay, because you need only opcode. There is no operand basically here. Okay, the operands are already stored in the registers, right? So it will take one memory location in the memory to store this byte. So it is 1 byte instruction. Okay. Similarly, your add B is also a 1 byte instruction. So you need only one opcode, that is 35H. Okay. So whenever the processor will fetch this opcode from the memory, it will decode it. So it will come to know that it has to move the contents of A into C. So there is already some data in A that will be just transferred to C. Okay, so this instruction is executed using a single opcode. Okay, so there is no other cycle basically. Only opcode fetch is the only machine cycle that you can say. Okay, similarly, if you have add B, so if the operation code for this instruction is 35H, so when the processor fetches this code, decodes and executes it, it comes to know that it has to add the contents of register A into B and put the data or the sum again in A. So that is again done by this 1 byte instruction. Okay. Now if you have MVIA comma 32H, if this is the instruction, it will require 2 bytes now. Okay. So first byte will be opcode, that is it can be anything. Okay, and the second byte is now your data byte. So when the opcode is fetched first, the processor will come to know that okay, it has to move some constant number into register A, and then it will ask for that or look for that number. So that must be supplied immediately after this opcode. Okay, first byte is your opcode, the second byte is a data byte. So it is a 2 byte instruction. Okay, now in this case you need two operations. One is opcode fetch and second will be a memory read operation. Okay, so opcode fetch cycle is the first part of an instruction. Okay, it will always be there. Okay, so which shows that how the opcode is fetched and how it is decoded and executed. Okay, so there are some instructions which are executed using opcode fetch only. You have not to do any other memory read or write operation. Okay, so opcode fetch is the only cycle that you have to do to perform that operation or to execute that instruction. But there are certain other instructions which may be 2 byte or 3 byte instructions. So in along with the opcode fetch cycle, you need other operations also. Maybe you have to read some data from the memory, or from you have to write some data into the memory, right? So now let us see the timing diagram for opcode fetch cycle. timing diagram of opcode fetch cycle. Now in the timing diagrams, everything will be specified in terms of the clock frequency. Okay, so one clock time period, we call it as 1t state. Okay, so t state, it refers to one clock period. Okay, so depending upon the frequency of this clock signal, you will have a clock with a particular time period. Suppose if your frequency is, if this frequency is suppose 2 megahertz, so what is the time period? It will be 1 by 2, it becomes 0.5 microsecond. Okay, and so on. Now when you have a opcode fetch cycle, it means in that what is being done, the opcode will be fetched from the memory. Okay, it will be given to the instruction register, and then from there it will go to the instruction decoder. The instruction decoder will come to know what is the purpose of this opcode, and the instruction will be executed. Okay, if it is single byte instruction, it will be executed in that cycle only. Okay, if it is not single byte, 2 byte instruction, then it will be executed in the next cycle. Okay, so what are the control signals now they are required for this? We have seen that, okay, you have a microprocessor, and then you have memory. So we have now a cycle which is opcode fetch. Okay, it means there is some data byte or some instruction, 8-bit instruction, which is stored at some memory location. The processor has to fetch this instruction, decode and execute it. That is what comes in the opcode fetch cycle, and this is the first part of an instruction. Okay, whether it is single byte or 2-byte instruction. So now you already know what are the communications. We will just plot them in a diagram. That is what is called as a timing diagram. Okay, so what the first thing the processor will do, you have address bus and data bus which are multiplexed. So the program counter will hold the address of the memory location where the opcode is stored, and after that the ALE signal will get activated. The lower 8-bit address will be latched. Okay, and then the read signal will go low because it is a logic 0 signal, and this memory chip will be selected. So whatever is the data at that memory location, it will come on the data bus and it will come inside the processor. Okay, so this all basically is done in 4 clock cycles. Okay, so you have, now we'll just say we have clock signal here now. Okay, so this is one clock time period. This is another clock period. This is another, and so on. Okay, so there are different clock cycles. You will see how many clock cycles will be required to execute this part of code fetch. Okay, so this is one t state or one clock cycle t1. This is another t2, t3, t4, and so on. Okay, now what are the control signals which are generated by the processor to execute this instruction? First we will see to that. Okay, so first of all you must have some data on the address bus which will be placed from the program counter. Okay, so you have your higher 8-bit address, that is A8 to A15, then lower 8-bit address AD0 to AD7. So a group of 8 wires here. Okay, similarly group of 8 wires here. So this will carry your higher order. A8 to A15, they will carry the higher order address, and A7 to your AD0 to AD7, they will carry your lower 8 bits. Okay, So this crossover point basically in the timing diagrams, it shows that at this point some data is being placed, okay, on the address bus. Okay, so let us suppose you have some operation code, like we have taken an example. You have a instruction move c comma a. The opcode for this is 4fh, and this opcode is stored at some memory location. Anything you can say, suppose it is stored at 2000h. Okay, so you have to fetch this code, decode, and execute. Now see how it will be done. So first of all, the higher 8-bit address, that is 20, it will be placed on the higher 8 bits 20h, and the lower 8-bit address, that is 00h, it will be placed on 8d0 to 87. Okay, now since there is a multiplexing, that these 8 bits, they are used to carry the address as well as the data in the earlier and the later part of this cycle. So to separate this lower bit address so that it can be used for data in the next cycle, so you have a signal, control signal, that is ALE, address latch enable. Okay, so this ALE signal is active high signal. Okay, it means during the first clock period T1 itself, this signal will go from 0 to 1. Okay, so this is a small pulse which stays for 1 for some time, and then it again goes back to 0. Okay, so during T1 or during the first clock period, the processor will first place the higher order address on that higher order bits, lower order address on the lower 8 bits, and at the same time during the first clock period itself, it will activate the ALE signal. So it will generate a pulse which goes from 0 to 1 for less than 1 clock, which stays or level 1 for less than 1 clock period. And during this time, during this first clock period, your lower 8 bits of the address, they are latched. Okay, so here now these 8 bits, so it will come on now A7 to A80. Okay, and for now this sorry, this is A7 to A0, and now for the next cycle it can become now a data bus. Okay, so AD0 to AD7 to AD0. Okay, and on the higher order, now see, since the higher order bits, they are used to carry the address only, so the data on this will remain constant for almost 3 clock periods. Okay, it is 20h, but on the lower address during the first clock cycle only, the ALE signal is activated. It goes from 0 to 1, and this address is latched. Okay, now in the next clock cycle, this bus is available to be used as a data bus. Okay, then what are the next control signals? Now say you have activated ALE, it has gone from 0 to 1, the processor has latched this lower 8 bits. Now these lower 8 bits, now they are free to be used as a data bus. So along with this, what you have to do, you have to now generate a control signal. Okay, but before the control signal, you have one more signal, which is input output oblique M bar. So this indicates whether it is a memory read operation or it is a input output operation. Now since you are fetching the data from the memory, okay, fetching the instruction in fact from the memory, it is opcode fetch cycle. So this signal must be kept at logic 0. Okay, so for the entire part, this will stay at logic 0. It will go from 1 to 0 in the very first clock period. So it indicates that it is at opcode fetch cycle. Of course, there are some other signals, status signals that we have discussed. Okay, you can use status signals S0 and S1. So they are also used to denote that it is a opcode fetch cycle. But to just avoid this, to make in order to avoid this complexity, I just negated one signal IO oblique M bar. So IO M bar will be simultaneously go from 1 to 0 to indicate it is a memory operation. Okay, and then you have to see another control signal, that is your read. You have to activate that now. Okay, so when this read signal should be activated, during the first clock or the second clock, because during the first clock the processor is busy in latching the lower 8-bit address. Okay, so you cannot generate the read signal at the beginning of the first clock period. It has to be run in the second clock period. Okay, when this address is latched, so it will remain high initially, and then in the second clock period it will go from 1 to 0. Okay, and it basically remains in this state, 0 state, for 2 clock periods, and then the processor again sets it to 1. Okay, now during this time when the read signal is activated, it goes from 1 to 0. The data which is stored, or the opcode which is stored in the basically memory, it goes from this memory to this data bus. Okay, so if the code is 4fh, so this 4fh will come now here. Okay, so you need to, so this almost takes 2 machine cycles. Okay, this takes 2 machine cycles to read the data from the memory. Okay, and then now see here, and in the last clock period t4, what happens now? This address is now unspecified here. Okay, so during the last clock period, that is t4, the processor will now decode and execute this instruction. Okay, so this is what is the timing diagram for opcode fetch cycle, right? So I will just again revise it so that it becomes more obvious to you. So we are taking example where we are saying that we have to copy the contents of A into C, and the operation code for this is 4fh, which is placed at a memory location 2000h. Okay, so you now already know what are the operations that has to be done by the processor. So it will first locate the memory location using the address bus. That address basically comes from the program counter, and then since the bus is multiplex, so the lower 8 bits they are used to carry the data as well as the address. So this address must be latched using the address latch enable pin of the processor. Okay, so once this address is latched, the processor will send a control signal read to the memory chip. The memory gets activated, and whatever is the data or the instruction at that location, that comes on the data bus, from where it goes to the instruction register and then the decoder, and that instruction is executed. Okay, so this is what we have done the timing diagram. So in the first part, we have placed the higher order address on the address bus, the lower order address on this lower 8 bits, and simultaneously we have activated, the processor will basically activate ALE. It will go from 0 to 1. So during the first clock period, this lower 8-bit address is latched. Okay, and the next clock period, these 8 bits they are free to carry the data. Okay, similarly your IO oblique mem, since it's a memory read operation, it goes from 1 to 0 in the first clock period, and the read signal is activated in the T2, that is second clock cycle. So when the read signal goes from 1 to 0, it remains in at logic 0 for almost 2 periods before it is again set to 1 by the processor. So during this time period, the operation code which is stored at the memory location 2000h, that is basically placed on the data bus. Okay, and in T4, now this and the last clock period, this 8-bit code will go inside the processor in the instruction register, and in this clock period it will come to know that okay, it has to move the contents of C into A. So in fact decoding and executing is done basically in the last clock cycle. Okay, so if it is a 2-byte instruction, it may be have to do one more operation ahead of this. In that case, the processor in this T4 state or the 4th clock period will just understand what is the meaning of this. Okay, but if it is a 1-byte instruction and it has to be executed using opcode fetch only, so all of that will be done in the T4 state. Okay, so you need 4 clock periods to perform this opcode fetch cycle. Okay, so for every instruction, whatever you execute, whatever the processor will execute, the first part is always a opcode fetch cycle. Now you can see how much time is basically required to execute this, right? So suppose if the clock frequency is 2 megahertz, the clock period is zero point 0.5 microseconds. So how many clock periods are required to execute this opcode fetch cycle? So you need 4 clock cycles. Okay, so what will be the total time? It is nothing but 0 0.5 into 4 microseconds. Okay, so this is how you calculate the time required for the execution of an instruction. So for that, what you should know, what is the clock frequency or what is the clock time period and how many t states are basically involved in executing that instruction. If you know that, just multiply the number of cycles with the clock time period, you will get to know how much time is required to execute that particular instruction. Okay, so next we will take one more case where we will see it's a 2 byte instruction, and along with the opcode fetch you have a memory read operation also, or a memory write operation also. Okay,